let's go on record. So yeah, let's talk about solar physics and so on. So we had this class last time, and I was here, and some people were not here. They were attending this prospective student thingy, and I was here and lecturing. And also the people who were here, they were not very engaged. So I was wondering why. And then I realized that the reason was that there were not enough equations on the slides. And everybody knows that the equations are what makes people think, right? Because the equations are complicated, and they make you think about stuff. Okay, so now jokes aside, I actually want to apologize for the fact that today we will have to go through some equations, but you don't have to know them, right? We will use them at some point, but you will just look up in the slides or in the appropriate books, and you will figure out what you need to use. So you don't need to know them by heart, but it's important to see some dependencies and so on and so on. So our main motivation here was to see how the spectrum is formed, and basically how this spectrum that comes out of the top of the solar atmosphere and reaches our instruments ultimately, how it came to be. And then we somehow hope, and we already feel intuitively that what we want to do is we want to reverse engineer this spectrum in order to figure out what kind of temperatures, magnetic fields, and velocities are in the solar atmosphere that we are observing, right? So when we obviously, our assumption is that, for example, if I'm looking at the flare and I'm looking at the quiet sun, the spectra is going to be different, and these differences between these spectra can tell me something. For example, and you already can somehow feel that some qualitative differences, but if we really measure quantitative differences and relate them quantitatively to the physical parameters, we can learn something about solar atmosphere. Basically, I put it here in bold, but I also use the quotation marks. We measure magnetic fields, velocities, and temperatures. The thing is that we don't measure them, right? I prefer to use measure for something that we use directly, like we have a meter, and then we measure the length of this table, and that sort of measurement. If I'm inferring indirectly from some sort of a model, some quantity, then I don't like to call it measurement, because it's model dependent, uncertainty, relationships are nonlinear, uncertainties are important, I need to know my noise, I need to fit, and so on and so on, and all these things are complicated. We sort of know now that, and Jose Carlos del Toro Iniesta says it very nice in his book, that the ruler for the measurement is the radiative transfer equation. That's maybe a bit too poetic for me, but we need to understand the radiative transfer equation and be able to solve it in order to understand these connections. And we somehow, I mean, we didn't agree on that. I imposed this on you, that spectral lines are the most important. But you sort of already know it, right? Like, we want to look at spectral lines to measure all these things. So we focused on basically calculating or inferring or deriving opacity and emissivity in the spectral lines. So now what comes next? Well, today we are gonna, yeah, Piyush, go ahead. No, sorry. Okay. Today we're gonna take a look at we're gonna look at the actual values that appear in these expressions for opacity and emissivity, and we're gonna go a step further. We're gonna calculate some optical depths and some source functions, and we're gonna calculate some spectra, and then we're gonna get familiar with some terms that you have already heard about, like depth of formation, contribution function, response function, and so on, so that we can sort of figure out how are we going to use them later in some sort of diagnostics, right? So I owe you a few slides from the end of the last class, which I wanted to finish in time since we got these things happening here. So basically, we started in, and this is something that I would like you all to always have somewhere when you are thinking about how the spectra is generated in one given atmosphere. So if I give you a model atmosphere, of course, I don't expect anybody to be able to write their own radiative transfer code. It's a lot of work, but you should understand basically what are the steps that you would have to take. And the first and probably the most cumbersome of all the steps is figuring out in this bunch of gas that is given to you how many atoms in which ionization and excitation state I have. So today we're going to go to the most simple example, which is just atmosphere consisting of pure hydrogen, which is relatively easy to solve under some assumptions. We're going to see that these assumptions are not good, and then later I'm going to hint, and next week we're going to talk in more detail what happens when you have multiple species and so on. After we have all of these things, then it means that we know for each spectral line and for each other transition, which I'm not talking about, but you sort of know from other courses that there are also other sort of transitions like ionizing transitions and so on and so on. we can calculate the relations of relevant atomic levels, and then we can, especially for our spectral lines, we can calculate the shapes of the absorption profiles, taking into account all the broadening effects, damping, and so on and so on. And what I want to stress here is that I need to do this for each point in my atmosphere. And when I say point in my atmosphere, it's because the atmospheres are basically some tables of quantities, right? And I need to do it for each wavelength that I'm interested in. So for example, if I want to simulate H alpha with, I don't know, 0.1 angstrom steps from 6325 to 6330, that's not 63, 65, 25 to 6530 angstrom, then I need to calculate my intensity and solve radiative transfer equation on each of these wavelengths. The same goes for different directions if you, for example, want to look at different angles. And then we basically need to calculate this opacity and emissivity, add them all together, solve radiative transfer equation, and we're going to get the spectrum, and that's where we are. And now just a little bit talk about how the source function for the spectral line behaves. So we know that the source function is the ratio between the emissivity and the opacity. And if you remember, I'm going to show them later again, but you remember that emissivity was proportional to the population of the upper level times a bunch of constants. And the opacity was this difference between the lower level times the Einstein coefficient of absorption minus the upper level times the Einstein coefficient of stimulated emission times a bunch of constants, and these constants are going to cancel. So if you were going to calculate the source function in the spectral line, it would look something like this, right? All these constants would cancel, and the most important thing for us is that the source function is wavelength independent. Okay? So the only wavelength dependency for emissivity and the absorption coefficient came from the line profile. We assumed, and sometimes that's not correct, but we assumed that this line profile is identical for the emission and absorption processes. It canceled, and our source function is wavelength independent. Okay. And this assumption that the absorption and the emission profile are the same is called complete redistribution. So when you sometimes hear about the complete redistribution, that is what happens. Okay. Right. So then what I can go even a step further, and I can say, well, okay, if now this point where I calculate emissivity and opacity is somewhere where the gas is very dense and when there is a lot of collisions, then also my ratio between emissivity and opacity needs to be equal to the Planck function. I don't know if you remember Kirchhoff's law. That's something that you learn in at the very end of your undergraduate optics course, which, surprise, surprise, I was teaching last semester. But do you remember Kirchhoff's law? Do you remember Kirchhoff's law, Niraj?
I think it's something to do with the conservation of energy, right?
Sort of. I mean, we mentioned it very briefly at the beginning of this 20th century optics when we consider how people derive the black body laws. So when you imagine that you sort of divide your cavity in two parts, and then their intensity need to be the same, and so on. Okay, we can discuss this further, but just take my word for it now that in the when the collisions are abundant and we have the so-called local thermodynamic equilibrium, the source function is going to be equal to the Planck function, and I can use this equality to derive the relationships between the Einstein coefficients, right? And this is pretty good for us because next week or the week after that we will want to calculate some actual opacities and emissivities from given models, and we will need these things, right? Because when you go to NIST web page and you want to get this data, the only thing that you will get is the Einstein coefficient for the spontaneous emission, or something called log GF or GF, etc., which is basically a classical equivalent of the Einstein emission coefficient, right? Oh, sorry, is this here? Cool. Okay, so I wanted to stress this thing here, and basically what I was showing you here in this example was the forward problem. So we had a simulation. These were the temperature and the line of sight velocity at one layer in the simulation. These were the line profiles coming from two different points. And then I told you that from the shapes of these spectra, we should be able to infer not only the physical distribution of the parameters at this layer, but also at another layer, right? Because the spectral lines are formed over the range of wavelengths, and they pick up the information over this range of wavelengths, and they tell us something about that. But however, the question is the following: we don't know this, right? In the real life, we don't have these maps. We want to obtain these maps, right? The only thing that we have is we have the spectrum for each point in the atmosphere. When we take our source cube, we can look at its wavelength at the time, or we can extract the spectra at the time. So now the question is the following. I consider one spectra, let's say this orange one. And from this spectra, I can measure various quantities. I can measure velocity, I can measure magnetic field, I can measure temperature. But we know that there is not one temperature, there is not one magnetic field, there is not one velocity in the atmosphere. It changes with height, right? So our question now is, when I measure this quantity, to which height it corresponds? And some of you already know some interpretations of this, and we sort of talked about this very briefly 2 classes ago, and I said, when we look at any astrophysical object, if it's so-called optically opaque, the radiation that we see comes from the optical depth at that wavelength equal to 1. Do you remember that? Okay. And that's the first and the simplest way to interpret something. Like, for example, when we look at H alpha line, it in the line core, the optical depth equals to 1 is somewhere in the solar chromosphere. So we look at the H alpha and we say, okay, if we measure velocities, if we measure temperatures, if we measure magnetic fields, these are the quantities, these are basically the conditions in the solar chromosphere. Of course, this is a gross oversimplification. H alpha is much more complicated than that, Momo. Don't give me that look. but in principle, that's our logic, right? And then people say these various things like Hinode lines, which are the iron lines around 630 nanometers, are photospheric lines. Magnesium 1b is a bit stronger, so it's so-called temperature minimum line. Calcium 8542 is even stronger, so then it's a lower chromosphere line. H alpha is even stronger, so it's a chromospheric line. Magnesium 2 H and K lines are even stronger, so they're transition region lines, and so on and so on. Or Lyman alpha special. So these are some things. However, it's not so straightforward. So today we're going to take a look into this line formation process, and we're going to, except for this optical depth equals 1, we're going to come up with 2 more complicated quantities. One of them is the contribution function, one of them is the response function, and we're going to see what they tell us about the line formation methods. Yes, Jared?
A comment, you were giving the example of the weak lines and then the little stronger line and blah, blah, blah. I mean, these are all lines that form at temperatures that are compatible. Because you go from 6,000 of the photosphere, a little less minimum, 10,000.
Yeah.
Once you go into transition region temperature or growth temperature, that's a different game.
Yeah.
You can do that.
Yeah, well, yeah, of course. When I'm going to mention it very briefly. Of course, this is not, for example, for corona lines, the ones observed by SDO, for example, as Aline presented to us in the journal a few days ago, the situation is completely different. Then it's not height anymore that determines things, it's mostly the temperature. And we will see now during the class how temperature influences the line formation. And we didn't see that so explicitly last time, but temperature is the most important quantity that determines opacity and emissivity of spectral lines, by far. And that's why different temperature, the first thing that you see, okay, you always can see lines moving left and right, but the thing that you see the easiest is that the hot regions are brighter, dark regions are cooler. And simple as that. Okay, so let's talk a little bit about what happens here. So I will have to repeat this many times because we need to use these quantities. So we know that basically our goal is to solve this equation here. We will have a hands-on where we will solve the radiated transfer equation numerically. We did it last year already, so some of you maybe remember it. I know that Niraj is even using that solution for his own research, which is a big plus. Extra 5 points for you, sir. So we usually cast it in this form. 5 points. So derivative of the intensity with respect to the optical depth at given wavelength is equal to the difference between the intensity and the source function. And I know that then that if I'm able to calculate the optical depth and the source function, my solution is going to look something like this, and this is what we call formal solution, right? So the only thing that I need to do after I have source function on a given grid is I need to solve this integral here numerically, and that's it. I get the intensity. And I'm going to show you how is that done sometime in the upcoming weeks. But today we're also just going to use some results of that without actually doing it ourselves. So what I want to show you today is we're basically going to take an example of a spectral line, and we're going to calculate all these relevant quantities and look how they change to the atmosphere. And we're going to see what this thing tells us. Yeah, this is not space. This is space. However, this was what I like to call macrophysics, right? So radiative transfer equation shows you what happens throughout the atmosphere on the macro scales. However, when we talk about the micro scales, we are basically taking into account what is happening inside of the atoms and molecules and ions and other absorbing and emitting particles, and then we need to calculate these quantities here, right? And this is so ugly because I wrote explicitly all the dependencies that appear everywhere, right? So emissivity and opacity, J and chi, depend on the position in the atmosphere, on the direction, and on the wavelength. And for example, emissivity is equal to the number of the excited atoms, local number of the excited atoms, which depends on the point in the atmosphere where we are. Obviously, the number of the atoms cannot depend on the wavelength, cannot change with the wavelength and the angle, times these constants here that are basically physical constants, times the line profile, which depends on the position, wavelength, and the angle. So, okay, why does it depend on the position? Well, we have seen before that it's some complicated function, which is basically convolution of the Doppler function times some damping profile and so on and so on. So this Z dependency should be obvious. Lambda dependence, of course, it's a profile, so it has to depend on the wavelength, right? Why does it depend on the angle? This is a little bit going ahead, but why does it depend on the angle?
Because the emission isn't necessarily isotropic.
Yes, that's true, but there is even one other reason.
It's because you have velocities.
Because you have velocities. So if you're looking at the direction, if for example the piece of plasma is moving upward and you are looking at the intensity propagating upward, you're going to have a blue shift. If you're looking from the other direction, you're going to have a red shift. So your profile is going to be shifted left and right, and its values are going to depend. So the value at given wavelength is going to depend on the direction. Okay, so this is just a bunch of equations to tell you how complicated these things are. As I said, you don't need to know them by heart. Eventually, if you start doing this, you'll learn them by heart. But of course, we won't do like theoretical problems where you need to derive these things. So our question is that basically what I talked about, what I said before. We infer something from the spectrum. To which layer of the solar atmosphere do I ascribe this quantity? So do I say, okay, I'm measuring chromospheric velocity, or am I measuring photospheric velocity, or temperature minimum velocity, or something like that? And to do that, we're going to pick one line, and we're going to pick this hardest line ever, just to show how wrong we can be when we do a simple approach, which is going to be H alpha. We're going to see how we obtain each of the quantities that we need. We're going to calculate the line profile and get the wrong result. Then we're going to switch to a simpler line, which is in this case going to be iron 63-2 lines, and we're going to study line formation and introduce some quantities there. Okay, so are you ready? Okay, I hope you are. So we're going to, first we need to consider an atomic model, atmospheric model. And what I'm showing you here is the, as I call it, infamous falsi. And I call it infamous because people love using this falsi model to study the line formation. Falsi is a so-called semi-empirical model, and the name Fal comes from the initials of the authors, so Fontainebleau, Avret, and Lesser. Avret is a famous radiative transfer modeler, and Lesser is his colleague, who together developed the radiative transfer code named Pandora, that was used to very painstakingly fit the whole, more or less whole visible and UV and infrared solar spectrum to to the observed one and obtain a model of the atmosphere. So what they ended up with was this distribution of the temperature plotted in red, and what I'm plotting here is, in principle, in the model itself is given the pressure, but what I'm showing you here is the total particle density, okay? Now, total particle number density, so number density of all the particles, not counting what is hydrogen, what are electrons, what are molecules, and so on and so on. And some other quantities which are not important for us now, on a grid of heights, right? So what we see here is we see the temperature drops very rapidly from some 9.5 thousand Kelvin to some 4.5 thousand Kelvin, and this is what I call temperature minimum. And then it rises, and it first rises slowly, and then it changes there's like an inflection point, and then it starts rising very, very quickly. And in some Falstein models, you have even more points here to the right, and temperatures going up to 100,000 Kelvin. We don't need it now, but they were able to infer that by studying various pieces of spectrum. Right. And the total particle density, be aware that this is in the log scale, okay? The blue line is in the log scale. It drops more or less linearly in the log scale. Why is that? Because of the certification, right? You probably did this exercise sometime in your undergrad where you assume that the temperature of, for example, Earth's atmosphere is constant, and then from that you can derive that the pressure needs to fall off exponentially with height, right? Exponential fall off in the log scale is linear decrease, and in principle pressure is directly related to the total number of particles. There is a lot of misunderstanding here when we talk about the number of particles. Okay, so people are always going to tell you that density and pressure are connected through something called equation of state. That is true. However, what I'm talking about here is the total number of all particles. And as long as the gas is ideal in terms that it's not degenerate, total number of particles times K times T is equal to the pressure of the gas. The only problem here is that I don't know how many particles I have, okay? So to illustrate this, if I have 1,000 particles of hydrogen, and it's completely unionized, these are 1,000 neutral hydrogens, and I have 1,000 protons and 1,000 electrons binded together in the atoms, right? However, if I have 1,000 particles in total of completely ionized hydrogen, that means that I only have 500 hydrogen atoms because it's ionized, so I have protons and electrons separated. And pressure in that case is going to be the same, but mass density is going to differ by a factor of 2. Okay, so maybe remember this from modeling of the stellar interiors. But modeling of the stellar interiors is relatively simple in this context because things are super, super much ionized. However, the gas can become degenerate and many things can happen. Okay, so the blue is basically something determining my pressure, and my pressure is more or less exponentially falling down because my temperature is more or less constant. Of course, it's not really constant, but it's changing by a factor of 2, which is not a big deal. Cool. So let's now go to NIST webpage, type hydrogen 1, type the wavelength of H alpha, and if you do that, you're going to get this output here. And there is no one line, there are like 1, 2, 3, 4, 5, 6, 7, 8, there are a lot of lines. Why are there a lot of lines? Why is there not just H alpha? What did we miss? So what's H alpha line? Transition from third to the second level of hydrogen. But what's missing? 3 and 2 are which quantum numbers? And principal quantum numbers. But the level configuration is determined also by L, by the orbital quantum number. In hydrogen, different orbital quantum numbers are so close that basically we see all these sub-levels with different L quantum numbers as one level. So we see one H alpha line, but strictly speaking, H alpha line is composed of many lines, right? And in principle, we can, since they're all so close, we can model them as one line, and sort of consider some mean properties of each of the levels. But if you really want to be super precise in the H-alpha model, especially if you want to model, for example, scattering polarization and stuff like that, you need to consider all these subtransitions. So this is the first complication story, right? You would think, okay, H-alpha is very simple, it's just hydrogen, proton, electron levels, 1, 2, 3, 4, 5, blah, blah, blah. It's not like that. Luckily, nice people at NIST did what? They have a separate entry for us who want to model H-alpha properly, and there is no lower and upper level configuration. There's only numbers 2 and 3, and some mean energies and some Einstein coefficient here. Okay, so from this we can take this. We know that from the upper and lower level numbers, we can calculate the so-called degeneracies. So if this is n equals 2, the degeneracy is going to be what? 2n plus 1, right? 2n squared, sorry, 2n squared. Yeah. So this is the degeneracy of this level is going to be 8, this level is going to be 18. Which means that I can put the electron there in 8 different ways, and here I can put the electron in 18 different ways. Okay. So now comes the first question. What I have here, and people who did homework last year remember that. Now what I have here is the total particle density. I can assume with some degree of reasonable doubt that all these particles, or let's say this is approximation 0, that all these particles come from hydrogen. So this is a mixture of neutral hydrogen, protons, and electrons, right? So now we need to find out what? We need to find out how many neutral hydrogen atoms we have in each of the points. And to do that, we're going to use something called Saha equation. Saha equation is an equation that comes from the statistical quantum, from the quantum statistical mechanics. And it basically tells you, for a given temperature, what's the relationship between two consecutive ionization states. So here with J index, I'm now again denoting some sort of population, which means some sort of number density, except now we are not talking about excitation stages, we're talking about ionization stages. So what this reads is, this is the number density of the atoms in ionization stage J plus 1, which I get when I ionize stage J. This is the number density of the particles in the ionization stage J. This is the number density of electrons. And it sort of makes sense that the number density of electrons enters this equation, because more electrons I have, easier it is to recombine things, right? And then I have various constants here. For those of you who are curious, lambda is, in a way, it's something they called de Broglie wavelength of an electron, and it depends on the temperature. And Z are the so-called partition functions. Partition function is sort of a generalization of the degeneracy or the statistical weight. This is like a statistical weight for the whole ionization state. And these are some things that you can, well, in principle you could derive it yourself, but there are convenient tabulated values for various temperatures and various species and so on and so on. And of course, this ratio has to depend on the ionization energy of my ion, right?
Ivan,
Either the ionization energy is, yeah, go ahead.
Is the denominator on the right-hand side there, is that supposed to be Z sub J?
It's supposed to be ZJ, you're right, yeah, sorry about that. I will correct that for the online version of the slides. Yeah, of course, this has to be ZJ, because otherwise it wouldn't make sense. Thank you. Yeah, so this, obviously, the higher this energy here is, the less ionized hydrogen in this case I'm going to have, because it's going to be harder to ionize it, right? I require more collisional energy. Cool, so I have to use this, but this is only one equation. I have 3 unknowns. I need to know, so for us, these are electron density, this is neutral hydrogen density, Nj, and Nj plus 1 is proton density. So, but from this, what else can I use to calculate all 3 quantities?
Well, the fact that the plasma is quasi-neutral means that the proton density and electron density are about the same.
Excellent. And then we said at the beginning that another quantity that is given to us is total particle density, and that's sum of all these three things. So I need to stop pressing the wrong button. So when we add these two more equations, what's going to happen here is that we're going to have that electron number density and proton number density is the same, and sum of all three densities is our total density. So we have three equations, three unknowns, but the system is non-linear. So even for a simple puny atom of hydrogen, which only has two ionization stages, the problem is already known. Now, imagine if we had multiple species. Now imagine that in addition to this, I had helium. Now I would have to write two more Saha equations for neutral helium and once ionized helium, once ionized helium and two ionized helium. Then this equation here would become more complicated. The total number of electrons would be equal to number of protons plus number of once ionized helium plus 2 times number density of twice ionized helium. And finally, this would be the total number of hydrogen atoms plus the total number of, the total number of hydrogen atoms plus the total number of helium atoms plus the total number of electrons is equal to total number of particles. And then I would have to solve that. And that, in that case, would become, so this system that I plotted, that I'm showing you now, you can solve it analytically. People who attended course last year solved it analytically, you just write a quadratic equation, you get it. But for more than one species, the system, you cannot solve it analytically anymore. You need to solve something that we usually call chemical equilibrium. And that's basically always the most cumbersome and most annoying part of radiative transfer calculations, because it's a nonlinear system that needs to be solved usually using something called Newton-Raphson iteration. And basically that's what we call equation of state. Because after that, when I see how many protons, electrons, neutral hydrogen I have, how much helium I have, and so on, I can add all the appropriate masses and I can obtain mass density. So from the temperature and pressure, I have obtained the mass density of my gas. Okay, and this is super cumbersome and super annoying. And what I did here is I just outputted the values from my code, right? I didn't actually do it. But in the hands-on, we can do this together using the simple approximation like we did last year. And then if we plot that, and what I'm going to plot now for start is just the spatial distribution of the number density of neutral hydrogen and ionized hydrogen, it is going to look like this. Does this make sense? So what are the things that you see? What are the things that characterize this distribution here? So as we say in Serbia, blue and yellow are gonna go out of your nose at the end of this lecture because there are at least 15 plots, which is just one blue line and one orange line. So yeah, go ahead. Dennis, you wanted to say something?
I mean, it makes sense that you have less neutral hydrogen as you go up the atmosphere since it becomes hotter.
But it doesn't always become hotter, right? Remember how the temperature goes? It goes down and then up. So this is not the ratio. This is really the total number of hydrogen.
Wait, the blue line is total number of hydrogen? Just
no, sorry. It's not the number of hydrogen, but in absolute sense. It's not like ratio.
Right.
Yeah.
I mean, like on a larger scale, like you expect less neutral hydrogen in the transition region than.
You mean the thing that the orange?
Like the general trend is somewhat correct. Somewhat.
I think the overall trend for the neutral hydrogen is going to be dominated by the overall gas density. It's like because that's just the fact that it's hydrostatically stratified.
Yeah. But what I understood that Dennis said is that it makes sense that the orange line is above the blue one here because hydrogen is mostly ionized high in the atmosphere.
Right.
Yeah, that makes sense. However, if we now went back to the plot, you would see the temperature here at the top of the atmosphere and temperature at the very bottom are very similar. Yet, at the top of the atmosphere, hydrogen is almost completely ionized. At the bottom of the atmosphere, it's not ionized, it's almost non-ionized. Why is that?
is a number density of free electrons.
Yeah, exactly. Because the problem is nonlinear, right? And in the less diluted, in the more dilute regions, recombinations are going to be much less likely, and I'm going to have much more ionized gases. And in the dense regions, recombinations are going to be much more likely, and I'm going to have less ionized gases. So you can, at some point, we will solve this equation, and we'll see what happens. What is interesting also is this dip here, and this dip of the ionized hydrogen exactly corresponds to the dip in the temperature, right? Yeah, Momo, go ahead.
Why is the ionized hydrogen so flat? It's the same amount of ionized hydrogen for 8 scale heights, like the same number density. Is this just how the model comes out?
It's just how the model comes out. I mean, this is also probably, it's going to be different in the real model because what I'm taking into account here is just collisions, right? The radiative ionization and deionization is going to polish the situation a little bit. But this comes out this way. I mean, we can go back. Let's see how the total number of particles changes. So we had a total number of particles here. It changes from 1,000 to 2,000. It changes by 2 orders of magnitude. And here from 1,000 to 2,000, it stays more or less constant. But that's simply because if you look at the blue line changes by 2 orders of magnitude. So electrons just stay constant because there's much more ionization as I'm going down. It just comes out that way.
Yeah, but just saying there's electrons out there is the same reason as there's why is there ionized hydrogen, right?
But I think
It's the same thing.
I guess it's because the temperature is going up, so the ionization fraction is going up, but at the same time the total gas density is going down, and they cancel this.
And yeah, exactly.
That's why. Because in the original model, like the non-LT model, they get something very similar.
Yeah, this is LT and only hydrogen. So.
Yeah, but you get, if you put the Fontaine-Law models, you get the exact same thing with all the non-LT that they put in.
Well, it's probably, then it just means that non-LT effects and LT effects don't differ hugely. They may be different by a factor of few, but then when you put it in log scale, it's more or less similar. Yeah. Simply, it turns out that the ionization increases by as much as the total number of particles decreases, so these two things cancel out.
In a real model, we would also have different electrons in the upper part of the atmosphere from the photosphere. So the photosphere is going to be almost entirely non-hydrogen electrons.
Yeah, to be honest, you have all the electrons here as well. I didn't really go and solve these equations. I just took the output of my code and plotted that. But the message stays more or less similar. Okay. But what I wanted to point out is this ratio here and this dip here. So because temperature enters, where does the temperature enter? It enters this. The most important dependence is this one. E to the minus energy over kT. This is very nonlinear dependence. And we're going to see much later why nonlinear dependencies are tricky. But we already see now here that the temperature doesn't change so dramatically, but the ratio between the blue and the orange line changes dramatically. Okay, cool. So now what I need to do next, when I know the number of my neutral hydrogen, I need to calculate my level populations of my level number 2 and level number 3, right? So what I'm going to do here is I'm going to write another equation from statistical mechanics, which is called Boltzmann distribution, Boltzmann excitation distribution. And what now I'm denoting, this is just a pedantic thing here, I'm writing, instead of writing Ni, which for us were these Nu and Nl, I'm going to call it Nji, which means number density of the particles in the ionization state J, in the excitation state I, which for us means at the level I. And it's going to be equal to what? Well, it's going to be equal to the total number of, it has to be proportional to the total number of particles in the ionization state J, statistical weight of that level. Statistical weight simply tells me the more ways I have to put electron in this level, more this level overall is going to be populated, times this factor here, which looks very similar to the one in the Zaga equation, which is E to the minus, this is now level energy over KT, and I have this partition function here again. Okay, so again, to use this G you will get from these databases, energy as well, K is the Boltzmann constant, temperature is in your model, and partition functions are given by very clever and kind people who calculate these things and publish so that we can use it later. So what I really want now to remember is that the reason why the temperature is the most important quantity is because it influences both the ionization and the excitation state in a very nonlinear, which means very dramatic way. So it influences opacity and emissivity hugely, and the spectra is mostly determined by the temperature. Okay, cool. So now I can plot the level populations. So this is now number of neutral hydrogen atoms in first, second, and third excitation state with the height. And we see again that the number of, first of all, we see that level 1 is much more populated than levels 2 and 3. And that makes sense because they're separated. So first and second level are separated by 10 electron volts. 10 electron volts is huge energy, right? Second and third level are separated by what, like 1.7, almost 2 electron volts, which is much smaller again. And you see that this variation is very smooth, while these variations here are non-monotonic, right? So they also have some local minimum. So here we have the same effect that we had with the ionization before. The temperature was so low, actually the temperature here in the temperature minimum is so low that even though the total gas pressure is higher, the populations of my H alpha levels are lower than higher in the atmosphere. And this is why people are going to sometimes say that H alpha is the line which is transparent to what happens in these regions here. And if you really go into H alpha formation and calculate something called the response function in non-LTE, which is a complicated task, you're going to see that response function doesn't exist in these regions here, and we can interpret it that H alpha doesn't see what is happening here. Its intensity is determined by photospheric things, its velocity and magnetic splinting and so on is determined by chromospheric things. But we will see that again when we calculate the opacity. So this is just something that I want you to notice now. The level populations dip here. The temperature is low enough, and it's not some insanely low temperature, it's not room temperature. It's 4,500 Kelvin. And still, because of the exponential, the populations drop this low. Cool. So now I can finally use these complicated equations to calculate these things. And of course, we're not going to now go and calculate each of the things separately. What I'm going to do instead is, actually what I did instead is I just took huge number of wavelengths, huge number of depths, and hard-coded the output of my code to give me these opacities and emissivities, and now I'm plotting them to you. And I'm going to plot you the line core, which is where the opacity and emissivity are the strongest, the greatest, and something that I call continuum, which basically denotes the contribution of everything except the line. So I said before that it's, yeah, sure, the lines are the most important ones, but there are other opacity and emissivity contributions, and in the spectral regions, when there are no lines, we have something that we call continuum, and that basically determines white light. So you could call it white. Okay, let's go. This is the opacity at two wavelengths. So now blue is the line core, where the line is the most opaque. Orange is the continuum, where it's less opaque. So I first want to point out this effect that we talked about before. So the opacity dips at the temperature minimum. So you would expect to some first degree approximation that the opacity scales with the density, right? Yeah,
What units is opacity?
Opacity is in centimeters to minus 1/centimeter. 1/centimeter. Yeah, so this is all CGS. I'm very sorry. Okay. I should probably change it to 1/meter, but what can we do? I should have given the unit. So the first thing that I want you to pay attention is that we talked about this thing here, and it really is small. So the opacity then rises and then of course falls again. The other thing is, let's look at the quantities. So I apologize for not giving the quantities. These are centimeters to -1. So the opacity of H alpha in the very depth in the atmosphere, in the core, is bare almost 1. So 1 per centimeter, it means that on average, the photons of this wavelength travel 1 centimeter before they are being absorbed. 1 centimeter. It's super, super small quantity. Even in the continuum, which is 4 orders of magnitude less opaque, the opacity is 10 to the -4 per centimeter, which means that something that we call the mean free path, which is 1 over opacity, should be 10 to the 4 centimeters, which is 100 meters. 100 meters is still nothing. We're talking about 2,000 kilometer scale. Okay? So this is justification why, very deep in the atmosphere, we can assume that things are all very local. So everything depends on the local quantities, because photons travel so short distances. They can't travel long distances, and they can't transform information, and they can't transport information and energy so much. Okay, and I just want you to see here that the line is much, much more opaque than the continuum, and we're going to see that later. It's going to translate into dramatic difference in something that we're going to call formation height. If I plot, stop doing that. If I plot emissivity, it's going to look very similar, right? It's going to look very, very similar, and somehow we are already feeling that it has to be like that. Can anybody tell me why it has to be like that?
You should follow the temperature.
Yeah, close.
Well, the temperature doesn't change that dramatically, and so the source function should be roughly constant.
Very good, exactly. So the ratio between emissivity and opacity is going to be the source function, which is going to depend on the temperature. It needs few more steps to justify that, but let's take a look at some other things. So obviously, looking at opacity and emissivity is cool, but what we want to take a look is the quantities that enter our radiative transfer equation, which means the optical depth and the source function, right? So let's try and plot the optical depth. So what I did here is basically I outputted the opacities, and then since I had the height and I had the opacities, I could basically calculate the optical depth myself. And we're also going to do that. You just write some approximation of the integral, and then you do that. So this is how the optical depth in log scale changes with height. Okay. So at the surface, they are both going to 0 because I impose them to go to 0. Okay. And then what I do is I just go downstairs from right to left, and I add contributions, and then I get these variations of the optical depth. So what is important for us here is I'm plotting this black line here, which denotes number 1, right? And now we can see that. Now we finally see the justification why we want spectral lines. We want spectral lines because tau equals 1 at 2 different wavelengths corresponds to dramatically different heights in the atmosphere of the sun. So for the orange curve, for the continuum, my log tau equals 1 is somewhere around 0 kilometers, which of course makes sense because in this model, 0 kilometers was defined as place where optical depth in the continuum is roughly 1, which is what we basically call photosphere. Okay? Sorry, chromosphere virus. In the blue, in the line core, we have the optical depth equals 1 line much higher, 1,500 meters, 15,500 kilometers. So this is already something that we would call mid-chromosphere or something like that. And this is what people mean when they say the optical depth. 1 lies at that and that height. And now we can better understand, oh, sorry, where is that? Now we can better understand plots in the papers like this. So this is from the last year's paper by our colleagues in Oslo and Stockholm, and they took a very sophisticated simulation of an active region and calculated, assuming very complicated and realistic physics behavior of H-alpha line and other lines. And what people usually plot in these papers is they give you a slice. This is now not a horizontal slice like the one that I was showing before. This is now a vertical slice of the solar atmosphere. And what you see here is X and Z, right? And these different colors, so blue, green, red, and orange, show you the lines where the optical depth is equal 1 to these corresponding wavelengths. Okay. And this shows a very important thing now, that when we have the atmosphere that is inhomogeneous, and this atmosphere is the atmosphere that we considered before, the Falsi model was inhomogeneous in Z. It didn't have X and Y because it was a 1D model. It assumed that everything is flat in X and Y. Now this atmosphere is inhomogeneous in all three dimensions. So what's going to happen now is that the optical depth equals 1 is going to be different for different X positions, because we are treating each of these little columns along X as a different atmosphere. So you see now that optical depth equals 1 varies with where we are. Okay? And this is what tells us something, and obviously here we see that there is no such thing as one height of formation. Height of formation depends on the model. This model is obviously, you see, there is something like specule here. So, and the color here is density, right? So darker regions are more dense regions. So there is something like a specule here, and obviously in the specule, since it's denser, the optical depths go higher, and so on and so on. Okay, does it make sense? You have seen plots like this before, right? Okay, yeah, cool. I'm also plotting source function just for the consistency. It is indeed identical at 2 wavelengths. And this is because I calculated everything assuming local thermodynamic equilibrium, which basically assumes that the source function is equal to the Planck function. The wavelengths are very close to each other. So always be aware of this pitfall. Yes, Planck function depends on the wavelength, but very slowly. Reasons why spectral lines exist is because the opacity changes by orders of magnitude on very small scales. So we see different black bodies at different depths of the atmosphere, right? Locally, for these 2 wavelengths that are almost the same, it's going to be the source function is going to be the same for both of the wavelengths, because I'm assuming local thermodynamic equilibrium, and it looks very much like the temperature. Can somebody justify why does it look like the temperature? Okay, I'll go back to the equation just to convince you. You can take a look at the equation actually, I'll think a little bit. So we have seen this at the beginning, right? What happens if HC over lambda KT is small?
That becomes linear.
Exactly. So if e to the HC over lambda KT is small, this is 1 plus HC over lambda KT minus 1, 1 and 1 cancel, and T flips up there. So for temperatures which are high, which means above a few thousand, and wavelengths that are, what's it gonna be? For the high wavelengths and high temperatures, which means above a few thousand Kelvin, and for wavelengths which are not in the UV, which are in the optical, the source function, LTE source function is going to be very roughly proportional to the temperature. So this is why we see that. For your exercise, you can plot this, and I think it was homework last year. You can plot these dependencies, and you're going to see that they become more and more dramatic as you go to smaller and smaller wavelengths. Okay, cool. So what do I want to plot now? Well, plotting source function and optical depth on the height scale tells us something about how the things behave on the in this canonical falsi model. However, what I really want to do in the context of radiative transfer equation, I want to see how the source function at the given wavelength varies with the optical depth at that same wavelength. And I'm going to plot this on this very useful plot here, which should make sense, but it doesn't. Right? It doesn't make a lot of sense because what does this tell me? Well, I see that the source function, first of all, basically what I did now is I took this y-axis and this y-axis and I combined it, right? So to see the difference. Now my x-axis is optical depth at 2 given wavelengths. This is source function at 2 given wavelengths. And this is very non-informative, okay? What we want to do instead is we want to calculate a new quantity, and that new quantity is going to be something that we call contribution function. Okay. So what we are actually looking at is the outgoing intensity, is this. And if we assume that the, oh man, I again omitted the explanation. Okay, so Dana is going to kill me. I always make some errors in the equations. So let's go back to the appropriate equation then, in order to not show you something that is wrong. So let's go to this one here. So this is our radiative transfer equation formal solution. Okay. What I'm going to assume that tau lambda is very large, because what I'm doing here, I'm integrating here over the whole atmosphere. And we have seen that tau lambda for the whole atmosphere is indeed very large. For H alpha, it went up to like 10 to the 5. For continuum, it went maybe to 10, 20, 30, something like that. It wasn't quite 10 to the 2, but it was more than 10 to the 1. So it's large enough because e to the minus 10 is already right, like 10 to the minus 3 or something like that. So it should be okay. So I can neglect this thing, and I'm going to get this integral, which basically goes from 0 to infinity. And then people said, well, okay, let's take a look at, let's define a new quantity, which is going to be this function under the integral, and we're going to call it contribution function. And that function basically tells us how much each part of the atmosphere contributes to this integral here. Basically, how much each part of the atmosphere contributes to the outgoing radiation. Okay, now I'm going to jump many slides, and I'm going to fix the slides before I put it online for later. So don't look at this thing up here. I'm going to define my contribution function as source function at given depth times e to the minus that depth. And now comes the tricky part. I'm multiplying again with the depth itself. And the reason why I'm doing this is because if you imagine the integral as a sum, okay? If I imagine integral as a sum, my tau spacing is not the same. It's basically logarithmic, right? So as I'm going to the surface, my tau bins, so to speak, are smaller and smaller, right? So Momo is,
but this should be d tau then, right?
Well, we could also write like d log tau, and then d log tau is going to be same bins, but then I need to multiply by tau, right? So take a look here. So these were the tau curves. So this was log tau here. Okay? Was this tau? Yeah, this was tau. Okay, so the contribution function basically tells me the following thing. It tells me how much each region contributes to the intensity. Obviously, the higher the source function is, the more contribution I'm giving, right? That makes sense. If the source function is bigger, I somehow contribute more to the outcoming intensity. However, the more optically deep this region lies, the more attenuated it's going to be by the time it reaches the top of the atmosphere. So this e to the minus tau makes sense. And then this tau lambda just comes to basically tell you that basically my bin at the top of the atmosphere contains much less material. So I also need to scale contribution by that. And my contribution, my bin deeper in the atmosphere contains much more material because my atmosphere is exponentially stratified, and I always take equidistant steps in height. Okay? So this, you can somehow relate this to the numerical formulation. Yes, Peter?
This doesn't make any sense.
So it comes, I think, at least mathematically, it comes from, if you take the integral and you transform it into an integral over d log tau. Yeah, that just comes from the variable transformation.
Yeah.
And I think the assumption is that integrating over log tau is roughly integrating over a linear scale. Yeah, it's height. So
like isn't like if you go back to the definition, so isn't like your first two factors and you give you the quantity that like, oh, that part of the atmosphere is like actually giving you that number. Why do you actually care about how much material do you have in that block?
To determine the emission measure. Like if you just have very few verified atoms, they're not going to emit a lot.
But didn't you already count that in that source term part?
No.
No.
No, the source function is, so you see that the source function looks like this, right? The source function just depends on the temperature. It doesn't know what is more opaque, what is more dense. One way to think about this is, imagine splitting the atmosphere, sorry, I'm rushing ahead. Imagine splitting the atmosphere in super small slices. In so small slices that I can assume that each slice contributes proportionally to its source function, but it also has to, because what is source function? Source function is emitted intensity per unit optical depth, right? So then the contribution to the emissivity, the contribution to the intensity from a given slice is going to be the source function times the optical depth, and deeper I go this optical depth for the same height binning is going to be bigger. Or the other way is simply to say, we want these things on the height scale. Height scale behaves similarly to the log tau scale, as Jonathan just explained. So then this extra tau needs to appear here. And now we can plot these contribution functions here to see how they behave. And now this makes much more sense. And these contribution functions peak at depths where we expect our lines to form. But now these also sort of tell us a bit more, like they tell us that in principle H alpha is sensitive to a wider range of depths than the convex sensitive. It's formed over wider range of depths than the continuum, and so on and so on. And in principle, for some extreme cases, you could get the contribution functions which are very wide, or maybe even double peaked, and so on and so on. For your exercise, now, we will go back to things that don't make sense, but for your exercise, trying to go from this S tau e to the minus tau times tau to the tau equals 1 rule in some way. So try to derive tau equals 1 rule. When I say tau equals 1 rule, I mean depth of formation is the depth where tau lambda is equal 1. So how would you obtain that? See what I'm asking? Like we say that, okay, so because you weren't listening, right? The contribution function is some function which varies with tau lambda. Depth of formation using the contribution function is the depth where contribution function peaks. See, so continuum contribution function peaks here, that's where the continuum is formed at 0. H alpha contribution function peaks here, that's where H alpha is formed around 1500 kilometers high. Cool. So the simpler way of doing this would be to say, well, let's just look where the optical depth is equal 1. And when we look here, we obtain similar conclusions, right? Optical depth equals 1 is more or less at 0 for the continuum, at 1500s for the line core. Okay? So can you now, using this equation, sort of derive the fact that contribution peaks at tau equals 1 at that wavelength?
You can take the derivative.
You take the derivative, but then the source function is going to make things complicated. If you just assume the source function is constant, you take the derivative, it's going to be e to the minus tau, derivative of this is 1, so e to the minus tau, plus minus e to the minus tau, right? This needs to be 0, and this is maximum for tau equals 1. So it's not really a surprise. I really need dramatic variations of the source function to depart significantly from tau equals 1. So probably when we go to UV, where things depend much more sharply on the temperature, and also regions where the UV things are formed, the temperature varies much more widely, the contribution function would make more sense than just looking at log tau equals 0, which means tau equals 1. Okay, cool. So this is how the contribution functions look like, and this is also something that if I give you tabulated opacity and emissivity, you can calculate fairly easy yourself. And the nice way to calculate it would be to plot it as a 2D plot. So now what I'm plotting here is, because contribution function, as we can see here, is going to be different at each wavelength and at each height, right? So it's like a two-dimensional quantity. So I'm going to plot it for all the wavelengths and all the heights in this way. And this basically can tell us where or how much each part of the atmosphere contributes to the outgoing radiation at which wavelength. So you see that in the line core, important is this region over 1500 kilometers. At the continuum, important are the regions about 0 kilometers, and so on and so on. Okay, very good. So this is one way to analyze your lines and to figure out where the things are formed. And then the next thing, finally, we can take this opacity emissivity, calculate the spectrum, and if we did this for our H alpha in the wings, it would look neat. Okay, not bad. When we go to the line core, completely the opposite with respect to the observation. Well, one of the assumptions that we made was wrong. Which one was that? What was the wrong assumption here? If I relax one of the assumptions and I do a slightly more complicated calculation, I can get much better shape. So which assumption that we made was wrong? There were not many, right? Well, Sacher-Boltzmann equations, right? We assume that ionization and excitation were completely determined by the local state of the gas, by the temperature. That is not true. And I spent some time convincing you 2 weeks ago that radiation itself can significantly alter the ionization and the excitation state of the gas. I can pump things I can excite atoms by aiming at them with a specific wavelength. I can ionize atoms and molecules and various other things by shooting them with appropriate wavelengths. So in this case, this is exactly what's happening here. This is in the core of what we call non-LT. So H alpha line is a line where these effects, the impact of radiation on the excitation state and the ionization state, is very important. And to properly get the shape of the line, we need to take that into account. We can't do that now. We will do that in another course. Probably not here. So we're going to restrict ourselves.
Evelyn, could you just go back and so there's two issues. There's the fraction of hydrogen that's neutral, and then there's the fraction of neutral hydrogen in the n=2 level that's ready to absorb. Which of those two is really responsible for the complete disagreement, or do they equal?
Actually the number of hydrogen in the level n=3 that is the most important.
Or n=3. You're right. Okay.
Yeah. Because what's gonna happen is that in order to have the same balance as we would have in the equilibrium case, we need to have certain amount of radiation to maintain that balance. As we go toward the top of the atmosphere, radiation starts, as we call it, escaping, and there is not enough radiation to maintain that balance, and the upper level, which means level n=3, depletes, and the source function drops. And when the source function drops, emissivity is smaller, and then basically the difference between the emissivity and opacity is going to lie under the Planck function, and we're going to get the absorption line instead of the emission line in this plot here.
All right, thank you. Yeah.
No worries. Okay, so instead we're going to take some simpler lines, still not perfect agreement. What I'm plotting here are the so-called Hinode lines. These are two lines of neutral iron, which are much more close to what we call LTE approximation. However, you see that there is a few aspects where they disagree with the blue line, which is the atlas here. I'm not going to go into that a lot. If you're interested, we can talk about it. Let's just say that file C is not sufficient to reproduce these lines, and these lines are not purely in LTE. There are some small ionization departures that are important to take into account. The best way to relate, to answer this question that I asked you before, is to calculate something called the response function. And now, I think I'm gonna just define what it is, and I'm gonna spend more time talking about it in the next class because we are running out of time. So I just want to emphasize the differences. So the contribution function was basically the measurement of how much each part of the atmosphere could contribute to the outgoing intensity. However, the argument for the response functions is that it's not that matters. It matters which region of the atmosphere your outgoing intensity is most sensitive to. Okay? And the way to formalize that is to calculate sort of a partial derivative of the outgoing intensity to various quantities at various depths, right? So what I'm calculating here and what I'm defining as the response function is, for example, let's say that my quantity is temperature. My response function to temperature would be partial derivative of the outgoing intensity to temperature at given depth. And then the more important the depth is at the given wavelength, this derivative is going to be higher and my response function is going to be larger. And the main difference between the response functions and the contribution functions is that contribution function simply looks at that integral and tells this is what matters. The response function actually makes the difference between various parameters. Obviously, I can calculate the response function to the temperature, but I can also calculate it with respect to density, with respect to the magnetic field, with respect to the line of sight velocity, microturbulent velocity, even abundance if I want. So in principle, I could define the response functions with respect to any quantity that I want, and I can assess how important that quantity at each depth and each wavelength is for the line formation. I'm going to tell this now, you try to think about it, and we're going to discuss much more on the next class, is the main reason for me is that the response function takes, in a way, takes all the nonlinear dependencies into account. So I'm sort of taking, in the contribution function, I sort of just assume, I'm looking where this function here is peaking, okay? And if I assume that temperature, velocity, all my things influence the intensity in a linear way, this is always gonna, my contribution function is gonna be great. However, they might not. The most drastic example is that, as I said, the contribution function is not making the difference between various parameters. So it could be that my line is completely immune on some parameter, right? Or very weakly sensitive. Let's say that I have a spectral line which is very broad and has very flat bottom, right? Then it's going to be relatively insensitive to the temperature, to the velocity, right? But still, my contribution function won't be able to tell me that. But if I calculate the response function, I will be able to see that thing. And often they're going to look the same. So these are now the response functions plotted. Okay, I'm sorry about this. Plotted for a different coordinates, plotted for something that we call continuum optical depth for these Hinode lines. And we see that they look sort of similar to the contribution functions that we have seen before. But if I plot them for various other parameters, they're going to look much, much more different. But we're going to leave this for next class. Any questions, any comments? Actually, before that, I want to say something. I made the joke about the coronavirus previously, which I don't think is funny at all. It was just a stupid blunder. So I apologize about that. go with your questions and comments. All clear? Okay, so basically what we were talking about today is we're going to go back to most of these things and clarify them. But basically what we wanted to talk about is that we wanted to see what are all the quantities that go into calculation of opacity and emissivity and how do things look for one example, right? And one way for you to use these things in your own research would be to say, okay, I want to use this line for measuring this. Then you take some model which you think corresponds to your physical situation. For example, if you're looking at the sunspots, you will want to use the atmospheric model appropriate for sunspot, maybe not the FALC. You can calculate various quantities here, like response functions, contribution functions, or just optical depth equals 1. Or in the end, if everything else fails, just use common sense to try and figure out which lines are stronger, which are weaker, and which regions, or which belong to which ionization stages, and so on and so on. And that way you can sort of quantitatively ascribe the quantities that you're measuring to depths in the solar atmosphere. We will see in a couple of classes that the only quantitative way to really do that is to perform something that we call spectral polarimetric inversion, that sort of retrieves depth stratification of parameters from the spectra, so you can sort of map the atmosphere in 3D. And this was all assuming that your line is formed in some sort of an atmospheric model. As Jana said before, when we go to some examples, it's going to become much less clear. Like, for example, helium-10A30 or coronal lines and stuff like that, they are formed in something that's above this atmosphere, some sort of loops or clouds or something like that. And then it becomes much harder, just by looking at them from above, to say where they are. Right? If you're looking at the cloud from above, you don't say it lies at 500 or 5,100 kilometers above the photosphere, because the things look the same to us from very far away. Okay, thanks a lot. Have a good weekend. And next week we'll do something practical. We will just finish all this story about the response functions to make them a bit more friendly to us, and then we'll go to actual calculations. Thank you so much.
Close that.